Good morning, ladies and gentlemen, and happy Monday. Today is March 30th, 2020. Welcome to another episode of Mr. Vasquez's Math Lessons. Today we're going to be starting Unit 7, which is all about circles. And we're going to start with our first lesson, lines, angles, and curves. This lesson is going to be a lot of definitions about the vocabulary we're going to be using when it relates to circles and math. Let's take a look. Our first activity is going to be a notice and wonder. Look at that circle. Look at that circle. Wow, what a circle. Now we're going to do some definitions. First up, we have a chord. Now, we're going to go through these words by showing you what is a chord and what's not a chord. This is a chord. This is not a chord. Chord, not a chord. So hopefully you can see based on these pictures, what do you think a chord means? Well, I'll tell you. A chord of a circle is a line segment, both of whose endpoints are on the circle. What happens when we kind of draw a line through the circle and put the endpoints wherever it intersects the circle. With this being said, what is the longest possible chord we could have in a circle? What's another word for that chord? Next up, we have arcs. Now, you might think you know what an arc is. You might be thinking of like the St. Louis arc or something like that. However, in math, we have this very particular meaning for what an arc is. This is what an arc is. This is what an arc is not. Notice you see that parabola-like shape and think, yeah, that's kind of what you might think of when you think of an arc. However, in geometry, we have a particular meaning for an arc. That's an arc. That's not an arc. An arc is the part of a circle lying between 2 points on the circle. So it's a section of the circle. If we just took a slice out, that would be our arc. Next up, we have the definition of a central angle. Hopefully, based on the name itself, you have a pretty good idea of what we're talking about here. These are central angles. Notice where the angle is located. These are not central angles. Notice where these angles are located. Central angles, not central angles. So, definition for a central angle is an angle formed by two rays whose endpoints are the center of a circle. Well, an angle is always made up of two rays, so really it's an angle where the vertex is on the center of the circle. Another bonus question for you. What is the measure of that central angle? Moving on to 1.3, arcs, chords, and central angles. Here we're going to apply a little bit of what we learned with these definitions, and we're going to prove a theorem, everyone's favorite thing. But first, a little bit more terminology. First, I want to talk about the measure of an arc is actually formed by the measure of the central angle, formed by drawing radii from the endpoints of the arc. So the measure of an arc is different than saying the length of an arc. When we talk about the length of an arc, you could talk about that in inches, in feet. Imagine if you have a track, a circular track, you could talk about how far along the arc you're running. However, the measure of an arc is actually based on the central angle. So we talk about the measure of an arc in degrees. So in this case, if we want to find the measure of arc CD, we would say the measure of the arc is 60 degrees. It's exactly equal to the central angle. So what is the measure of arc DB? Well, DB would have to be 120 degrees because angle DAB would have to be 120 degrees. So whatever the central angle is the measure of the arc. We could also talk about arcs that are bigger than just a small one angle. For these cases, we often want to use 3 points to name the arc. So in this case, it says, what's the measure of arc CDB? That means you start at C, you go through D, and you land at B. The measure of that arc would, of course, be 180 degrees, half a circle. So now we're going to get to our proof. Here we have a circle with two chords drawn in that we're told are congruent. And they have these little arcs cut off. We have the orange one and the blue one. The question is, what do you think is true about those two arcs? Now, first, we're going to draw in lines from the arcs to the center, create two triangles, because we're always dealing with triangles. And we're going to take a look at those central angles. And the question is, how do we think those two central angles compare? Well, what can we say about those two triangles? Since I drew in the radii, I know that all radii in the same circle have to be congruent, which actually means that every single side of those triangles are congruent, which means the triangles themselves are congruent by side-side-side triangle congruence theorem. Classic. And since the triangles are congruent, that means that the two angles making up the central angles must also be congruent, because corresponding parts of congruent triangles are congruent. Takes you back, doesn't it? So since these two central angles have to be the same, that means the measures of those arcs must be the same. The orange arc and the blue arc have the same measure. Therefore, anytime in a circle, if you have two chords that are the same length, if they are congruent chords, then they have to cut off the same measure arc. And that's proof. Now, we just have one more thing to do before we wrap up this lesson. Are you ready for more? That's right, we're doing the Are You Ready for More? Proof that the perpendicular bisector of a chord goes through the center of a circle. It's actually a pretty straightforward proof. It's something that you're going to be seeing a lot, so I definitely wanted to address this question here. Now, first, we're going to have to draw a circle, and we're going to have to put a chord through it. And this picture pretty much reveals everything we need to know. But there you have it. So if you just draw a chord XY going through the circle, it could be anywhere through the circle, we know for a fact that the line segment Hugs and Kisses and line segment Yo are the same length because they are radii of the same circle. That means that because the center is the same distance apart from the endpoints of the line segment, it must be on the perpendicular bisector. That's right, this goes all the way back to Unit 1, one of the first definitions that we learned in this class, coming back here in the final unit of the book. If it's the same distance apart, it must be on the perpendicular bisector. And we see this isosceles triangle kind of being formed here. We know the perpendicular bisector perfectly cuts the isosceles triangle into two congruent parts. You're going to be seeing this type of picture a lot as we go through this unit, so I wanted to introduce it here. So that wraps up our lesson for today. As always, if you enjoyed this video, make sure to hit the like button, share, and subscribe. And until next time, stay safe out there.